Hi, and welcome to the 10th lecture in my series on Introduction to Quantum Theory and Technologies. In the last several lectures, I've been talking a lot about how quantum measurements work, and we saw that quantum measurements are kind of a probabilistic process, and in fact, there's many different ways that you can even do a quantum measurement because in quantum mechanics, you can actually have many different types of orthogonal bases that you can measure in. A measurement isn't exactly just a single process. You can actually do sort of an infinite amount of measurements depending on what setting you have your measuring device on. So what I want to talk to you today is about how you actually interpret or extract information from that probability distribution and hopefully get some information about what kind of state the particle is actually in. The basic idea of what we're talking about in this lecture is sort of summarized in this slide here. Um, so the point is that the quantum wave function actually should contain all the information there is to know about the system. The wave function is really a kind of a summary of all the information that is known about the particle. And that means that if you want to know any kind of physical property, for example, the position or the velocity or angular momentum or the energy of the particle or something even more complicated, then we should be able to deduce that from this wave function. The question is, so how do we actually get that information exactly from these measurements that we've been talking about? Roughly speaking, we've got this particle, goes inside this box here, and it spits out all these different probabilities, as we've seen in the last few lectures. So how does this guy here actually take those probabilities and make something kind of meaningful from these values? So for example, maybe he's interested in what the energy of the particle is. How do we actually work out what the energy is, for example? So let's to sort of illustrate this problem, let's sort of make up a particular problem. So this is obviously not a completely general formulation or general situation, but this I think will sort of illustrate the point of what we're going to see later on. Let's consider this sort of scenario. So that say that we've got this particle, this red particle here, and suppose there's many boxes that are all in a line, like on the ground somewhere, and the boxes can be in any one of the boxes at a time, right? Well, classically speaking, that's the situation, right? This red particle, for example, here, it's in box number 3, which is labeled according to like where it is in this line. It's in position number 3, so the particle is at position number 3 in this case. Classically, of course, the particle can only be in one box at a time. But as we know from quantum mechanics, the particle can actually be in many of the boxes or even all the boxes sort of all at the same time. And the way that we would write that quantum mechanically is something like this, where we've got this wave function which describes the state of the system. These states 0, 1, so on up to n are the states of the particle being in one of these boxes. State 0 means the particle is in box 0. State 1 means the particle is in box 1, and so forth. And quantum mechanically, we are allowed to have some kind of linear combination of these, so we can form a vector out of all these different states. And so a completely general quantum state that you can write down is written in this form, where there's some coefficients a, and the label of the box is x, and so these numbers a x specify the type of quantum state. Right? So if you're thinking that this is a sort of a bizarre example, and you can't possibly have a real particle that's in real life size boxes if you laid them on the ground. Well, we can certainly have a microscopic version of this. So for example, there's been recent experiments that have been done. The groups, well, one group that did this was the group at Harvard. And what they did was to do exactly something like this, but a microscopic version. What they actually do is they can focus laser beams into kind of a narrow spot. And if you choose the laser and the type of atom correctly, then you can actually suspend little particles or little atoms at like the focal point of these lasers. So the atoms are actually kind of just hang there, they sort of suspended. And so if you had like one atom, then it could be in any one of these focus spots. And so you could make a kind of a microscopic version of this. Right? Okay, but anyway, we'll work with the this kind of schematic example that I drew here. Okay, so then suppose we say, okay, I want to know now, where is the particle? So as we know, if we try and measure the position of the particle, then what's going to happen is that, so we've got all these detectors, we've got a detector for each position here. And if we try to measure where the particle is, and it's in this kind of superposition state, then what's going to happen is that it's going to probabilistically go into one of these detectors. So it'll be kind of random, so it won't go into the same detector every single time. So maybe on this time it's gone into detector number 5, but if you've got some superposition state, then maybe on the next round, it'll be in detector number 1, and so forth. So it'll be kind of random. And so what we'd do is we'd repeat this experiment many times, and then we get like a histogram of which detectors, or basically which box we detected the particle in. So I've just made up some random histogram here, so it might look something like this, right? And the number of counts that you get, so if you repeated this 1,000 times, then some proportion of that 1,000 times would be in box number 0 or 1 or so forth. And the number of counts that you get would actually be proportional to the probability that it's supposed to come in as predicted from quantum mechanics. And so the probability is supposed to be the modulus square of this coefficient here. So say if you ran it 1,000 times, so this m tot would be 1,000 in my example here. So if this probability here was something like 0.1, then you'd say I got 100 counts in this box number 0, and maybe this is like 180 or something. Okay, so that's basically what would happen. So what we've got here is like some kind of probability distribution, but this still hasn't really answered the question of where is the particle. So the question is, obviously it's not really even a proper question, actually. So we know that quantum mechanically it's where is, it's actually the wrong question, right? The particle is everywhere, distributed between all these different boxes. So there is no singular answer to say where is the particle. But actually, we do know how to deal with something like this. And for example, if you have some kind of random kind of particle, not quantum, but just a regular random particle, or maybe a random object like a die or roulette wheel or something like this, then we know that even though it's random, we can actually say certain things about it. For example, we can say on average the particle is so this place, or on average the the number that you get on the roulette wheel if you average between all the different cases is something like 30, or on average the die, if you averaged over all the different cases that you get on the dice, then it would be something like 3, because 1 is the lowest, 6 is the highest, so you get something in the middle, right? So we can do basically the same thing here. So in our probability distribution, then if you get some distribution like this and say there's only 7 cases, then on average you might get something like the average position of the particle is maybe somewhere where this red line is, because that's sort of the average of where this probability distribution is. So we can say on average the position is at 4.3, but then actually it's quite random, and it'll come out at 0 or 7 or some other places a lot of the time, right? So that is basically how we handle you know basically the question in a quantum mechanical setting. So even though we can't say where is the particle as a with a definite answer, we can say, well, on average it's here, or alternatively we can give, not alternatively, furthermore we can actually give more details about what this distribution kind of looks like, and another quantity to characterize the probability distribution is things like variances or standard deviations. And this basically tells you, what the spread of the probability distribution is. So we can say on average the position is at 4.3, and in fact the spread of this, or standard deviation, is going to be equal to, I don't know what the value is, but maybe it's like 3 or something. So it's 4, average 4.3, plus or minus 3. So the variance, of course, gives you basically how wide this distribution is. So the wider the distribution is, the larger the variance. And if you want a kind of a numerical figure on exactly how wide this distribution is, then you take the standard deviation. Okay, so this is basically how we handle giving observables, or values of observables in quantum mechanics. So the position is just one example. We can actually do this for any kind of quantum measurement. So if we were interested in things like the energy, again, the particle may not actually have a specific value of the energy, just like this case where the particle didn't really have a specific value of the position, right? So you can have situations where the energy is also kind of probabilistic. So sometimes the energy comes out a bit higher, sometimes it's a bit lower. But again, we can say, well, all right, it's kind of random, but on average, the energy is 3 joules, right? And then we can talk about the spread of the energy. We can also do the same thing with momentum. So, maybe the momentum is now not exactly a precise value, but you can also talk about averages of momenta, and also like the variance of the momentum and so forth. Okay, so that's basically the idea of how you deal with it. You basically deal with it in the same way that you deal with it statistically, right? Okay, so let's sort of formalize this idea a little bit. So I'm going to make this a little bit more kind of abstract. So let's talk about some kind of general observable Q. So this Q could be anything, could be position, momentum, energy, whatever physical observable that you might be interested in. And at this point, I'm not really going to find Q mathematically. I will do later on, but at the moment, what we know is that basically whatever this observable is, so if it's energy, position, whatever it is associated with some definite types of states. Okay, so there's some states where for particular states, it's got particular values, right? So in the previous example that I had here, so the states that I was talking about here were actually the position states, right? So this was a particular state where the position of the particle was some fixed value. So basically, if it's in this state, like state number 3, then that means that the position is exactly at 3. It's not like 2 or 4 or 9. It's exactly at 3. That's basically the property of that particular state. That's just kind of how we defined it. This state has a position equal to 3. Okay, so in this more sort of abstract way I'm describing it, there are some definite particular states, and each of these states has some particular assigned value to it, right? And in the case of the position, this Qn is like the position of the particle. So, so for example, that's basically what I've written here. So if the states are like associated with the definite positions of the particle, then basically in this case the Qn would be like the numerical values of the position, like 0, 1, 2, 3, 0 meters, 1 meter, 2 meters, things like that. But we could equally do this for other types of observables. So if we could have these as definite values of energy, right? So say we were more interested in measuring the energy, where the observable here was some energy of the particle, then what we do is we take all these values, states, which have a definite energy. I haven't really told you how to do that, but I'm basically, well, I'm telling you here that it's possible to actually define particular states with definite energies. And those states have the numerical values. Q are the numerical values of the energy. So then, we can extend this to any kind of observable, like momentum or angular momentum, or anything that you really like, right? So there's some particular states with definite properties, and that's basically what is this Q thing here. So then, if we have the state in some kind of superposition of these states that we just were talking about, then what we do is we go and measure it. We go and measure it with respect to that basis, this n, and then we'd of course find that the probabilities come out with the modulus squared of these coefficients. And then if we wanted to talk about so what's the average value of this Q thing, position, energy, whatever it is, then what we do is we take these probabilities, we would multiply it by these values that we defined, and then we just sum over all the different cases, right? And these probabilities, of course, have to add to 1. So we just end up with this sum, or if you like, we can write it in this way. This is the modulus squared of these coefficients, and so we got this sum with the an mod squared multiplied by the qn. Okay, so simple enough. That's basically a general formulation for how you do measurements. Okay, but what if this observable R didn't actually have the same kind of states as the way that we wrote this state? So we learned before that actually there's sort of an infinite number of ways that we can take the some basis, right? So this R has some some particular basis, and this might not necessarily be exactly the same states that I've written my quantum state in. So you might think, okay, so what do I do in that case? Because in this case, it was kind of easy because I could just read off the probabilities that I would get for each of these states here, n. But in this case, this R might not have the same basis as like this state. So for example, just to give you a quick example, that maybe this R was written in some basis where for the qubit, remember those states that we were dealing with, where the plus state was this 1 over root 2, 0 plus 1. And then there's also the minus state, which is basically the same state, but then with a minus sign, so same, but then here would be a minus. So what if R was written in terms of this basis, but then my quantum state here, psi, was actually, written as something like, A0 with the state 0, and then A1 with the state 1, right? Okay, so this is in the previous page, these states were basically the same states as here, so it was kind of simple, but in this case, the R might have a different basis to the state. Okay, so in this case, the procedure is we have to modify our procedure a little bit because the basis is different, but more or less conceptually it's the same. So what we do is we first have our state written in terms of this, say, the 0, 1 basis, so whatever our original basis is. Then we'd have to convert that to the same basis as we write for the R. So, for example, we'd have to convert our state here into the plus minus basis. And then once we've written that, then the job is pretty much done because then we just follow the same procedure as what we were doing before. So we just take these B coefficients. So notice that these coefficients B are going to be in general different from the coefficients that we wrote in A. And so we take these B coefficients because that's the same basis that we're talking about. The probabilities are the mod squares of the B's, not the A's. And then we just do the same thing as we did on the previous slide. We take the average of this observable R by multiplying the probabilities by these R's. So this Rm is the definite values. So here I should have written Rm. Okay. So the definite values are m for some basis of those. And then the average value would be equal to the bm mod squared times by rm, and then you sum over all different cases. Okay, so that's more or less the general formalism for how you come up with sort of observables and averages in this case. So actually, so that is it. But actually, there's a really neat way of calculating this, which often makes calculations quite easy, and it actually makes all this kind of notation that we're dealing with a little bit clearer why we are using this notation. So right at the beginning you might have been wondering, why are we using these these kind of funny square bracket things, these Dirac bracket things? Why don't we just use like the normal notation for vectors with the arrow on top or something? This is basically where all that comes together. So if you're curious on why we are using this notation that we're using, then this is the section for you. All right. So okay. So another way we can actually calculate observables is actually by constructing this observable operator, right? Okay, so the way that we calculate this thing, so previously I didn't really define what Q or R was, right? This Q that came up before. I didn't really define what it is, but here it is. So what we do is we have this outer product of these states with the definite values. So for example, the position or the energy or whatever it is. So these are the states with the definite values. We take the outer product of that with itself, and then we weight it by whatever value of the observable it is for that particular state. And this is basically our definition of the observable operator. Okay, so once we've written it like that, then a way that we can actually calculate the expectation value or the average value of this Q is actually just in this red box. So it looks really simple. So the left-hand side is just my notation for the average. So just read that as average value of Q. And that happens to be equal to this particular combination of conjugate and state vectors with this newly defined operator Q. So basically, it is the conjugate vector psi multiplied by the this operator that we just defined, Q, and then multiplied by the state. So written in terms of the row and column vector ways. So here would be the state. So we've got some states here. It's a row vector, and then this Q thing would be some operator. So it's actually a matrix. So this has got entries. It's like a square matrix like this. And then this state vector is a column, so it's like a it looks like this. So it's basically column vector multiplied by this matrix multiplied by the row vector, and this gives a number because when you multiply a vector by a matrix, you get another vector. So then it's like a column vector. And then when you multiply the column vector by the row vector, then this sort of goes on, up, and then this gives a single number. And we need this to be number, of course, because we can't have, the average value being, like a vector or anything like that. This is a specific number that you want to get for a particular state for a particular observable. Okay, so um, okay, so why is this so? So I've just told you that in fact we can calculate the averages also in this way. So this is sort of like a second way to calculate the average. So the reason why is because, so let's just go and evaluate this thing. So I've defined this Q and here's my state. So let's just go and just do the maths and work this out. So first let's work out what Q times psi is. So Q times psi is, so Q is, that's just this definition here, and psi is just the state here. And notice that when I write these things, I should be careful to not use the same index twice, because this sum is talking about all the terms inside the bracket here. And if I used n here, like n, not n prime, but n, then this sum would be start summing over stuff in here, and that's not what we want, because this q thing and this psi thing are sort of, they're separate objects, so they should have separate index labels, otherwise we're going to get mixed up. Right? Okay, so that's the definition of the Q and the psi. And then what we can just do is use the fact that these are states and they're all orthogonal to each other. And this thing is actually equal to either 1 or 0. It's only equal to 1 if n prime is equal to n. And if n prime is not equal to n, then sorry, n prime is not equal to n, then it will be equal to 0, right? So that means that the only term, say in this sum, that will survive is when n is equal to n prime. So then that actually kills one of these sums, and we actually get one, just the single sum where this n prime is equal to the n, and this is what we've got left over. Okay, so that's the first part here, the q times the psi. Now let's go and complete this thing. So now we multiply whatever we got here by the conjugate vector. Okay, and so the conjugate vector is you take the star complex conjugate of these coefficients, and you take the conjugate, the row vector version of this n, and we go and do this multiplication. So again, n prime and n has to be equal, so we use the same kind of identity here, and one of these sums collapses, and what we get is something that looks like this. It's an times an star times qn, and an times n star is an mod squared, and that's exactly what we got 2 pages ago. Just to prove it to you, there it is as we had it before, there it is now, and we use the right hand side to calculate this, so that means that they are always the same. So that actually shows that you can actually calculate the average value using this kind of neat formula. It's kind of one of the main results of this this lecture. And this, maybe for the first time, you can actually see the sense in actually using this kind of notation for the vectors, right? So whenever you want to take like an average, and this is sort of like the average symbol, you can kind of immediately sort of fill in these gaps here and say that, well, if I want to calculate the average, then all I need to do is kind of sandwich these states by the measurement operator, and I can always just go and calculate the average. And so this is basically why we are using the notation that we are. Of course, we also need to use this kind of notation to distinguish between the the regular vectors and then the conjugate vectors, because they are they play different roles, as we've seen. Okay, so that's that's sort of a alternative way to calculate averages. Now, what about that example that I gave a couple of slides ago, where the operator, say the R operator, didn't have like the same basis as the state, right? Well, at least the way that we've written the state they didn't have the common basis, right? What happens in that case? Well, the answer is basically exactly the same. So we don't have to really change anything. Our formula still works. So if we want to calculate the average of R, then all we do is we go and sandwich this state with R, despite the fact that they're not in the same basis or whatever, and we can just keep the same formula. So so this is basically a formula that kind of always works regardless of what basis you've happened to kind of write your state and operators in. So the proof is a little bit lengthy, but let me just show it to you. Just I don't really expect you to sort of know this from the top of your head, but you should be aware that this you can write these things equivalently. Okay, so how does this work? All right, so let's just go and multiply this R times this state psi as we did before. So here we go. We got this R times the psi. Here's our definition of this R. So again, we've got these values of the observable with the outer product of the states. Okay, and the big difference here is that these things which are written by M what I mean by that is that they are not in the same basis, so I can't use that uh, simplification that I did before, where the n and the n prime, if they're the same, it's just 1 or 0. Basically, I can't use that trick in this case, right? All right. So in this case, so we've got this thing m and n, this inner product between those two things, and this is basically as simple as I can get this formula. So it's got two sums, whereas before one of the sums can't been cancelled. It just only one of the terms in the sum survives, so we can get rid of one of the terms. And we've got two sums. It looks really ugly, and but that's the best we can do with this expression. Okay. Then we multiply this guy here, the r psi, multiplied by the conjugate vector. All right, so that's the conjugate vector. That's this ugly looking thing which I calculated in the previous line. And then we can actually do this, just sort of rewrite this a little bit. So first let's take the inner product between the n prime and m. So we get that thing there. And I'm not sure how versed you are in dealing with these expressions with the sums, but they work a lot like integration, right? So you might be actually kind of even more familiar with integration than with these sums, but they work in exactly the same way. So that means that, for example, say you got like integrals like, dx, dy, and say you had, okay, let's put a third integral here just for fun. Okay. So for example, let's say you had like a function of x, y, and a function of, say, just z here, right? Okay. So because this function here is actually independent of the z integration, you can actually pull this outside the z integral because it actually doesn't depend upon the z. But the gz you cannot pull outside the integration here. So you could write this, for example, as something like dx dy, and then f of xy multiplied by the integral of z, and this is gz, and you can actually, even though this has got like 3 integrals, you can actually just multiply the result of this integral, multiply that with the result of that integral, and basically you can just do those separately, multiply the results later. So in the same way, you can actually swap like the orders of these summation signs, just in the same way you can swap the order of the integrals, as long as the things inside it don't depend upon the variables that the sum is going over, right? Okay, so for example, here we've got some term here which depends upon n prime. This is dependent upon n prime, this is dependent upon n prime, but these guys are not dependent upon n prime. Okay, so that means that we can actually just do that sum and don't really worry about this sum here at all. But we can't pull this one outside of this sum here on the left because that's actually got an m there. So it's good to take it as far left as possible, but in this case, that's as far left as it will go. This one, the sum over n, this is only dependent on the sum over n. And this thing is not dependent on n or n primed at all. So actually, this can go outside the bracket. So I've just sort of reshuffled these things in such a way as to make their dependence on each of these sums clearer. Okay? And actually, what you'll notice here is that this thing here is actually exactly the complex conjugate of that thing. So in fact, we can actually just write one of them and then just take the mod squared, because that's what complex conjugation actually means. So we can write this in a slightly simpler form like this. Okay. All right. Okay. If you haven't done all these sums and things like that, if you're not familiar with them, then don't worry too much. Well, if you can follow it, then all the better. Okay. So let's see. Then let's compare this to the thing that we had 3 pages ago. So that's over here. So what I said over here is that we need to first write the average of R, then we need to first write this state in the same basis, work out what these coefficients B were, and then you just take the mod squared of the B's and then multiply by R. Okay, so that's great, but I never really told you how to work out the B's, right? So I just said go and work out the B's, but I didn't really tell you how to do it. So here's how you do it. So this is actually maybe the most commonly used quantum mechanical trick basically ever. So you keep on using this trick over and over and over, so that yeah, it's a very, very useful trick to know. So if you want to be like a quantum expert, then you might like to get some practice with this. So the basic idea is this very, very simple identity, which is that the identity matrix, sorry to use the same word twice. So the identity matrix is the matrix where you have ones just along the diagonal and zeros everywhere else. And it's kind of very obvious from the structure that if you multiply any vector by I, this identity matrix, then you'll just get the same vector, right? Because it's basically like the one vector in of the vector world, right? Okay. So the key point is that actually we can construct this identity matrix using actually any basis that we like. So we could write this in terms of the n vector. So this was like, say, the original basis that the state is given to us in. Or we can actually write it also in this new basis M, or in fact any other set orthogonal basis set. And you can actually work this out. So for example, if you took the states, the basis like 0 and 1, so that's for the qubit, that's one basis. We can construct the identity using 0, 1. But you can actually also construct it using the states plus, minus, or any other orthogonal set of orthogonal pair of vectors. Right? Okay, and then what we do is we choose this representation of the identity. Then we kind of use this identity here, where we say that the state is equal to identity times the state, all right? Multiply this thing into there, just substitute that expression into there, and then voila, we have an expression where we've rearranged, once we rearrange it, once we've rewritten the state A in terms of the new basis set of M. So this thing in the brackets here is equal to Bn. So we can actually get a pretty simple formula for calculating the values of Bm. And then finally, we can just compare the two things that we've got. So from what we had over here, we notice that actually that thing in there is exactly what Bm is. So we can actually just replace that with Bm, and that exactly is the definition of the average value of R. So So basically, we've gone in sort of a sort of a long journey, but we've actually kind of proved that we can actually work out the average value of R simply using this formula here. So yeah, so this is the point I was making before. This actually makes clear why we're using this so-called bracket notation, because we can always work out what the average of some observable is just by sort of sandwiching these two, uh, the observable operator by the state. And we can do things like calculate variances, standard deviations, exactly in the same way. So if we wanted to work out the variance of a quantum state, variance of a quantum observable with respect to a quantum state, then it would be equal to, of course, the average of R squared minus average of R all squared, and that's just equal to that according to this formula. Okay, so now let me just go on to talking about particular types of operators that that sort of often come up, particularly with qubits. So in what we're going to do, we're not actually going to be doing so much on sort of physical um, properties, although that's actually exactly what you can do with this kind of theory. We're mainly going to be working with qubits because this is a course on quantum information, and the qubits are the analog of the bits, and we're going to build up to doing things like quantum circuits and things like that. So the most relevant observables for qubits are these things called the so-called the Pauli operators. So now, unfortunately, this doesn't really have a really very good kind of physical intuition to it. So it is somewhat abstract, despite the fact that this lecture is supposed to be about sort of physical observables that you can that you can extract information about. But this is basically the closest that you can have for these types of qubit systems. Okay. So there are for a qubit there are three commonly used observables. That doesn't mean there's only three. In fact, you can have as many as you want in a way. But there are kind of three which most which are most important, if you like, and these are imaginatively called the X, Y, and Z Pauli operators. We'll see why it's called that in a few slides. But basically, how these work is that because there's only, we're dealing with a qubit system, there are only ever two outcomes, right? So our measurement only is like either, there's only two particular outcomes to the measurement. So the value of each outcome is always taken as plus or minus one. Okay. Um, this could be some other choice, but this is just the choice that we sort of ended up with. So this is as sort of as good as any, if you like. And the difference between the Pauli X, Y, and Z operators is that the basis states that are used are different in each case. So in the case of the so-called Pauli Z operator, the basis states are your standard 0 and 1 states, right? In the case of the Pauli X operator, your states are these plus and minus operators that we already encountered in some previous lectures. And the Y operator has also these states plus and minus Y, which are defined in this way. Okay, so all right, that's just three different operators. So firstly, why define it in this way? Well, So for example, if you are making a measurement of, say, this qubit, then we learnt from before that we will get either 0 or 1, and the probabilities that you get are, in this case, alpha squared or beta squared, beta mod squared, alpha mod squared. And in this case, this average value of the z, which we can work out just it's simple enough to see in this example. So in this case, this is the value of this outcome is defined to be +1, and the value of this outcome is defined to be 1. Sorry, is defined to be -1. So according to our rule of how we calculate the averages, what we do is we multiply this value by the probability that it comes out as. So it's 1 times alpha mod squared plus -1 times beta mod squared, and that's basically how you get this formula. So that's the average value of z. So what does this number tell you? So firstly, because we know that the these coefficients are normalized, that means that the biggest that this could be is when, and keep in mind that alpha squared and beta squared, these are both positive numbers. So the biggest that this could possibly be is 1, because the biggest that alpha can be is 1, because if alpha is bigger than 1, this is not normalized, right? So the biggest that alpha could be is 1, and then in this case beta is 0. So in this case, the average value of z is 1. And if the smallest that z could be is when beta is 1 and alpha is equal to 0. So that's sort of the flipped case. And so basically this z operator thing kind of tells you, in terms of the magnitude of these alphas and betas, which way is it most biased towards. If it's 1, then it is mostly biased, like it's mostly weighted towards this 0, and if it's -1, it's mostly weighted towards this this other state here. So that's basically why it's chosen in this way. It could have been chosen in a different way, but that's basically how you interpret it. Okay. Now we can also work out these averages in a different way. So here I just did it like the first way, which was like you weight these factors by the probabilities, and then you add over everything. But we can also do this new way that we worked out, which was you multiply the state by this observable operator, or the matrix version of it, and then you calculate this quantity. So what is this quantity in this case? Well, we can easily work that out just from the definition. So for example, in this case of the z, the way that this is defined is you take the observable, the particular states that we are defining, the basis states, and then we weight it by the values. So this value was +1, this value was -1, and so our matrix is like this. In the case of x, our basis states, the plus and minus states, the value of this is +1, the value of this is -1. We can go and calculate the matrix expressions for this using the definitions. We subtract these ones. What happens is that these terms cancel out, and then these terms will be like 1 minus 1 and divide by 2, so that gives 1. So this one is like off diagonal in with ones, and for the y's, there's some i's floating around here. Again, these diagonal terms cancel out, but these i's actually survive, and you get i, which is minus 2i divided by 2, which is -i, and you get an I here. So these can be used in order to calculate the average values. So let me give you a kind of an, an example of this. So you might like to sort of pause the video and try and work this out for yourself before I sort of show the answers. So that's why I've got the blank version here. But so the question here is, using this state here, which is actually the general form of the qubit state that we worked out several lectures ago, calculate the expectation values of the Pauli XYZ operators using our standard kind of, way of working it out. For example, X is like the state multiplied by the operator multiplied by the state. Okay, so so that's the exercise, and the answer is here. So we can go through this sort of one by one. So the average value of the Z operator, as I said just a moment ago, is equal to this. And so you can just go through and do your matrix multiplication. I used the matrix version of calculating this. You can also equally do it using the Dirac bracket notation if you like. Okay, but I did it the matrix version here. So you just go through and do your matrix multiplication. You do this multiplication, then you get this here. So what's happened here is that the sign here is flipped because of this -1 here. So you get that. And then you perform your matrix multiplication of this vector with the conjugate vector, which gives the number. And here the exponentials cancel out, and you get cosine squared minus sine squared, and we can just use a trig identity to simplify this a little bit, and you get cosine theta. For x, the difference here is that the x actually kind of flips the vector from the top to the bottom, right? So when you multiply this guy with this matrix here, the top and the bottom kind of flip, and then what happens is that you do this multiplication, then you get e to the I phi plus e to the minus I phi term. That term there gives you should be a cosine, yes, cosine phi. And then we can use our trig identities of sine, the double angle rule, to get this to be sine theta. And for y, you get something similar to the x, except you got an I here with an extra minus sign. These things now have to subtract, and because you're doing this the difference between two either the I phi's, you actually get a sine instead of cosine. The i's actually cancel off when you do the calculation, and you just get that. Okay, so okay, just straightforward calculation if you like. But what some of you may notice about these things, cosine theta, sine theta cos phi, sine theta sine phi, that this looks a lot like the spherical coordinates, right? And and this is exactly why actually we've chosen this parametrization actually in this way. So why did I choose this theta over 2? Why didn't I just choose theta? It's actually because it will make it match exactly these spherical coordinate angles. So I'm not sure if you're familiar with the spherical coordinates, but just in regular old 3D, if you use spherical coordinates, so for example, if you got x, y, z, so forget about quantum mechanics for a minute. We're just living in regular three-dimensional space, like we really are. So x, y, z, we can actually use like spherical coordinates in order to parameterize the location on the sphere. In fact, we literally do this for latitude and longitude on the Earth. So between those two angles, we can pinpoint any position on the Earth, right? And the way to convert to the x, y, z coordinates is using basically this formula, where the x position is sine theta cos phi, y position is sine theta sine phi, z position is cos theta. In fact, so normally there's a radius. You multiply all these things by the radius of the Earth, but in this case we've got a radius 1 sphere, so there's no radius here. And because these things are exactly the same as the the way that we interpret the coordinates of a sphere, this makes actually a really nice way of kind of visualizing the state of a qubit. So normally a state of a qubit, it's a little bit abstract. What are all these complex numbers? How can we understand what all the different states are? Well, this is actually the way that you normally visualize states. So basically, we visualize every state of a qubit to be on a particular location on the sphere. And this is a purely sort of, geometric parametrization. There's nothing really in real space here. It's just how we kind of can sort of mentally map the states of a qubit onto a sphere, right? Okay, so um, it just so happens that we can we have the sort of the same kind of structure uh, on a sphere as all the states that a qubit has, right? So basically, like, each point on Earth could be viewed as a particular state of a qubit, and the way that we convert that point on the sphere into the quantum version of it is basically using these angles here. So whatever your coordinates on the sphere are, we can actually turn that into some kind of analog of the quantum state. Okay, so that sort of wraps up this lecture. So as usual, if you have any questions, and please don't hesitate to contact me, and we will leave it there for this week. Okay, so thanks for your time, and see you later.